Hello student, today we are going to see the next chapter of the physics, that is the magnetic effect or the magnetic fields due to electric current. Now see, in this chapter, first of all see the introduction. You are familiar with the Oersted experiment. That is, Oersted first discovered that magnetic field is produced by an electric current passing through a wire. If a magnetic needle is held in close of a current carrying wire, then what happens? It shows the deflection of magnetic field circling around the wire. That means if you put this current carrying wire in near the needle, then what happens? It deflects. And from this, we are going to see there's a magnetic fields due to electric current. Now see the most important or familiar, that is the right hand rule or right thumb. Imagine, you have to imagine that a current with your right hand with the thumb pointing in the direction of the current, and then your fingers curl around in the direction of the magnetic field. That means if you consider this current carrying coil is put in your hand at that position in your right hand, then at that position this curl finger indicates the directions of the magnetic field and this straight thumb indicates the directions of the current which is flowing through that conducting wire. Now next, that is the magnetic force. What is this magnetic force? That means when this particle or when this charge is under the magnetic field, then there is the one force which is act on that. First upon, we are going to see the concept for electron. Therefore, the magnetic force which is indicated by the sign Fm on electron with a charge minus E moving with a velocity v in a magnetic field. Here we can consider this is the charge here with velocity v, and then we are going to see the force in general. This is the equation for the electron, that is this B bar is nothing but the magnetic field, and the force which is act on this magnetic field on that electron which is equal to minus E V bar into B bar. In general, for a charge Q, the magnetic force will be, that is the F bar which is equal to Q into V bar in cross B bar. This is the vector product. We can write that is the QVB sine theta, where this N bar which is called as the unit vector, where this theta is nothing but the angle between this V and B, and this N bar is unit vector in the direction of the force. If the force F is 1 Newton, what is the force 1 Newton? There is the definition of acting on the charge of 1 coulomb moving with a speed of 1 meter per second, and it is perpendicular to B, that is the magnetic field, then we can define the unit of this B, that is the B is equal to, rearranging this above equation, we can find out the equation for this B. B is equal to F divided by this QV, where V is the charge, V is the velocity and Q is the charge, and force, that is the F. Again, in terms of the unit, this force having the unit, that is the Newton, and this meter per second. Therefore, finally we got this magnetic field is equal to Newton second per centimeter per coulomb meter. Therefore, this unit is also called as the Tesla, and this is the SI unit of the, this is the SI unit is called as the Tesla T, and which is equal to 10 raised to 4 Gauss. If now see, this is very important concept. We see what happened when the magnetic field is applied, what happened when the electric field is applied. Now, if the both electric and magnetic field both are present, then the net force on the charge Q moving with a velocity V bar, which is called as the Lorentz force, that means this total addition of this total force, which is called as the Lorentz force. Therefore, F bar is equal to Q into, that is the E bar, that is the nothing but the electric field, and this plus Q V bar cross V bar. That is the magnetic force. Therefore, the total force is equal to the electric force plus magnetic force. Suppose if the velocity V bar of a charged particle is parallel of the magnetic field B, then the magnetic force is 0. Because this equation sin 180 therefore is equal to 0. If the charge is stationary, that means V bar is equal to 0. Obviously the force which is equal to 0, even if, but V bar is not equal to 0. And this is the all concept about this, the Lorentz force, that is the force because of the electric field and because of the magnetic field. Now see the cyclotron motion. Cyclotron motion is very important concept of this magnetic field. This a particle with a charge q moving with a velocity v bar in a magnetic field. B bar is directed into the plane of the paper. Here this particle is put here. According to the Lorentz law, the magnetic force on the particle will act toward the center of the circle of radius r, which is also called as the centripetal force. And this force will be provided, that is the centripetal force, to sustain a uniform circular motion. That means the particle revolve in a circular motion because of these two forces. That means this magnetic force is balanced by the centripetal force. And here we got the equation, that is in mathematical term, that means this electric field is balanced by the magnetic field. That is QVB is equal to mv square divided by r. Now rearrange the equation. This mv is nothing but the momentum. Therefore, instead of this mv, we can write down this p. P is nothing but the momentum, which is equal to qb bar. Again, see the construction, that is the cyclotron, which is invented in 1934. The cyclotron is a charged particle accelerator. That is, it's accelerating charged particles to high energy. Now see the principle of this. The magnetic field puts the particle ion into circular path, and a high frequency of electric field accelerates it. Frequency of revolution of charged particles. It is independent of its energy in a magnetic field. Here these are the two D's. This is D1 and this is D2. Then we are going to accelerate these particles into these two D's, and then we are increasing the radius of these particles. Now see the construction. Cyclotron consists of two semicircle discs like metal chambers D1 and D2, which is also called as the Ds, like this D1 and D2. A uniform magnetic field B is applied perpendicular to the plane of that disc. An alternating voltage up to 10,000 volt at a high frequency, that is the 10 megahertz, which is applied to these two discs. Then the next step is positive ions are produced by a gas ionizing source kept at the point O in the between of these two discs. The electric field provides acceleration to the charged particles. Then see how the working of this cyclotron, that is the working. Once the ion is emitted here, it accelerated due to the negative voltage. Then first upon ion is positive, then it attracted towards the positive terminal. It accelerated due to the negative voltage of a D and performs a semicircular motion within the D. Whenever the ion moves from one D to the another D, that means you can say that D1 to D2, then it accelerated due to the potential difference between the two Ds, that is the positive and negative terminal. These are the potential difference between the two Ds, and again perform semicircular motion in another D. Hence, the ion is always accelerated. Its energy during this, that means positive to negative, negative to positive, during this energy is increasing. That means the radius of the circular path also increasing, making the entire path as a spiral. Now see the calculation. Time period of ion moving in a semicircular path. From equation that we have the equation mv is equal to qb bar. Therefore, the time, that is the t, is equal to 2 pi r divided by v. That is this is the distance divided by velocity. The distance is nothing but the circumference, and so 2 pi r divided by v. Therefore, putting these values of, we get here this m2 pi into r divided by qbr. Then again rearranging this equation, rr get cancelled. Therefore, the remaining equation is that t is equal to 2 pi m divided by qb. And the frequency of revolution, that is the cyclotron frequency, which is equal to, that is the f is equal to inverse of this time. Therefore, from this equation, we can easily find out the frequency of revolution, that is the qb divided by 2 pi m. With the help of these equations, we are finally find out the kinetic energy of the ions and protons will be. Why there is a protons? Because we are here going to take the positive ions. So we can say protons will be, that is the kinetic energy, which is equal to 1/2 mv square. Therefore, we have the equations of this mv square, that is the q square divided by q square b square, because this mv, here this formula mv. Therefore, putting this value in this equation, q square b square r square divided by 2m, and this is nothing but the final energy, that is the final energy of that ion, which is proportional to the square of the radius of the outermost circular path, that is the r, which is called as the external r. Now see, this also depends upon the cyclotron, the magnetic force on a wire carrying a current. Here this is the consider, here the first upon in this concept we are going to see the straight wire, and then we are going to see the curved wire. Consider a straight wire of length, that is the field b bar. Here this wire here, and perpendicular to the wire coming out, that is this b bar, that is the magnetic field is perpendicular to this wire coming out of the plane of the paper. Let a current I flowing through the wire, that is the I, Vd is the drift velocity of the conduction electrons. See here, this is the Vd, that is the drift velocity. This is the magnetic force acting on that conducting wire. Again, if the charge q flowing across the plane pp, here this plane pp, then in time t, it will be q is equal to it. That is the basic formula of the current, that is the charge per time. Therefore, q is equal to it. Therefore, q is equal to, that is the q is equal to I, that is the I, that is the t, L divided by Vd, that is the drift velocity, that is the time, that is the distance divided by velocity, so that L divided by Vd. The magnetic force Fm on this charge, which is given by, we have the equation, that is the Fm, that is the magnetic force, which is equal to Q. We know that the basic formula Q into V bar cross B bar, but here we are considering the drift velocity. So instead of this V, we are going to take V bar D. Therefore, again putting the values of Q. What is the value of Q? Q, that is the IL divided by VD. Again B, where this vector product, where solve this vector product, therefore B into VD sine theta into n bar. N bar is nothing but the unit vector, which is equal to IL. Therefore B sine theta, where theta is 90 degrees. So perpendicular, so 90 degree. Therefore n, that is the unit vector, where this n bar is the unit vector. And why this is here sine theta? Because the vector perpendicular to both B bar and VD in the direction of F bar. Again, we have the equation, that is the magnetic force, which is equal to ILB into unit vector. This magnetic force acting on the portion of the straight line having the length L, like this. If B bar is not perpendicular, Suppose B bar is not perpendicular, then what happened? This F bar M, which is equal to, that is the magnetic force. This F bar M is nothing but what? Magnetic force, which is equal to I into L bar cross B bar, where this L bar is the length vector directed along the portion of the wire of length L. That is, this is the equation for this F bar. Now see the arbitrarily shaped wire. Consider I is the current flowing through the segment of an infinite simile length dl. Now total length is suppose dl, but here we are considering the small part of this wire. Here we are considering the small part of this wire. Therefore, the magnetic force due to perpendicular magnetic field B bar coming out of the plane of the paper is given by, therefore D into F bar is equal to IDL, that is the I into, what is this DL bar? DL is nothing but the small part of that arbitrary shaped wire. We are just considering for the small parts first. Therefore IDL bar into B bar, that is the magnetic field. The force on the total length of the wire, therefore which is equal to, we are going to take integration, suppose here dl, again dl, that means considering all this dl, and this is nothing but the length, therefore the fm bar, which is equal to integration, that means what is the meaning of that integration? That means we are considering all this dl, that is the all the length of that arbitrary wire. So d f bar in f bar m, which is equal to, again this I common, therefore dl bar into B bar. Here this equation is D is equal to this, so that we have take here this integration dl bar into B bar. If B is uniform over the whole arbitrary wire, suppose this B bar is uniform magnetic field, then finally we got the magnetic field acting on that arbitrary conducting wire, which is equal to I integration dl bar into B bar. Next, that is the force on a closed circuit in a magnetic field. For a closed circuit, that is the C, here closed circuit F bar, which is equal to I integration dl bar into B bar. Integral is over the closed circuit C. For uniform, for example, first we are going to take the uniform magnetic field. So Fm bar, which is equal to, this is integration over a closed surface. So here take the integration like this. These circles indicate over a closed surface. Therefore, I dl bar cross B bar. Therefore, finally this I constant term, therefore in bracket integration over a closed surface dl bar, that means we are going to take all the length of that arbitrary wire. So dl bar into B bar. The term in the bracket is the sum of the vectors along the closed circuit, and hence it must be equal to 0. And finally, for uniform magnetic field, this magnetic force which is equal to 0. Now see the torque on a current loop. The current carrying wire loop is a rectangular shape like this here, this A, B, C, D. This is the rectangular shaped wire and is placed in a uniform magnetic field in a such a way that the segments AB and BC of the loop are perpendicular to each other. This AB and BC are perpendicular to each other. Now see from the right hand rule. From the right hand rule, the pointing fingers of the right hand rule, the pointing finger of the right hand show the direction of the current. Okay, then let the middle finger indicate or show the direction of the magnetic field B. Then the stretched thumb shows the direction of the magnetic force. Using the right hand rule here, we can find out the torque or the current loop here, that is the force which is acting on that rectangular shaped wire. Here again we are going to see this diagram. Consider the rectangular loop ABCD place magnetic field B such that the sides AB and CD are perpendicular to each other. Now see in diagram, the side AB and CD are perpendicular to each other. That means to the magnetic field also B bar, but the side BC and DA are not. The force on the side BC will be, therefore F of 4 is equal to, here we are taking the force which is acting on that AB, then BC, and then CD or DC. These are the force acting on that corresponding rectangular wire. The force on the side BC will be F bar 4, which is equal to IL2B sine in bracket 90 minus theta. The force on the side DA will be similarly F2, which is equal to IL2B sine 90 minus theta. Thus, the F2 and F4 equal and opposite. That means having the same magnitude but opposite in direction, so they are cancelled out. And so this F2 and F2 bar and F bar get cancelled. The remaining forces, that is the magnitude of the force F1 bar and F3 bar on this rectangular coil we are going to see. Then the torque tau due to the forces. Now the F2 and F4 get cancelled because having the equal and opposite magnitude. Equal magnitude but opposite direction. F1 and F3 will then be, therefore tau is equal to this because of the F1 and because of this F3. Therefore IL1B by 2, that is the here half portion. Here we are taking the half portion from here and half portion from here. So that this 1/2 L2 sine theta, I L2B 1/2 L2 sine theta, and solving this we got I L1 L2 B sine theta. If the current carrying, here we take only the one turn of the rectangular wire, but if there are n number of turns, if the current carrying loop is made up of multiple turns, that is the n, therefore we have to only multiply this equation by n. Therefore tau dash is equal to, tau dash is nothing but we are taking the equation for n number of turns, and so we multiply this equation by n. So the tau dash is equal to n into tau, therefore which is equal to n into I, which is equal to I L1 L2 B sine theta. Again this L1 L2 we can say that A, therefore tau is equal to n I A into B sine theta, where n is the number of turns, I is the current which is flowing through that wire, and A is the area, and B is the magnetic field, and sine theta is the angle between them. Therefore hence A is the area, and in this way we can find out the torque for n number of turns having the rectangular coil. In this way today we stop here, and in next session we are going to see the next concept of this magnetic field